Okay, so we've looked at the ideal gas law, but now we're going to look at specific laws that were created from the ideal gas law. We kind of did this before, so you don't necessarily have to know the names of these laws, like the one we're going to talk about today is Boyle's law. You don't really have to know what that is exactly, because you can create Boyle's law by using the techniques that we learned last week. So Boyle's law is a comparison of pressure and volume. And if you remember from last week, we said if we're going to compare two values, we're going to separate them onto one side of the equation. And actually, pressure and volume are already separated for us. So we can create Boyle's law. Once you separate them and you move the other stuff to the other side, since this stuff's not going to change, and only these are going to change, this is what we're going to compare. This is what we're putting on one side, and the stuff that doesn't change goes on the other side. So Boyle's law actually says P1 V1 is equal to P2 V2. Okay. A little illustration for you. I'm going to draw a balloon. I know how much you love me drawing balloons. Okay. Not too bad. Let's put some molecules in here. They are flying around in any direction, right? Let's give them little arrows. Not that it matters, but the point is they're bouncing off the walls of the balloon. They're going everywhere. And every time they hit the wall of the balloon, they create pressure. Okay, so this is pressure and the balloon is holding a certain volume. So let's think about this. If the volume were to start to shrink and get smaller, those particles are going to bounce off the wall even more. So if the volume shrinks, the pressure should increase because those molecules are going to be in a tighter spot. They're going to bounce off the walls more, create more pressure. Now, on the same thing, what if the balloon expanded and the volume increased? So the volume would increase. It gives these molecules more space. They won't hit the wall as much. They won't create as much pressure. So what you're going to see is that pressure and volume are inversely related. And if you remember our little rule from last week, if the two values are on the same side, then they will do opposite things. If they're on opposite sides, they will do the same thing. So since pressure and volume are on the same side, they'll go opposite, meaning if pressure increases, volume will decrease. If pressure decreases, volume will increase. When the two items are on the same side, they will do opposites. So here's your perfect example. All right, hopefully that makes sense. Like I said, you don't necessarily have to memorize this, but if you're comparing pressure and volume, you will have to just know to isolate the pressure and volume and then make a little equation out of it. We're going to do two examples, and then I'm going to set you up with two homework questions that are on Schoology, and they're going to be the exact same thing. And I'll just have you type in the answers for me. Okay? It's not too bad. It's just going to be a quick multiply and divide, and you'll have your answers. So let's start. Now, you're going to see some units that you might not be familiar with, but, oops, sorry about that. If you do, don't worry too much. Just read the problem and understand what it is. So I'm going to underline some stuff. 128 kPa, 101.3 kPa, and 2.11 L. Well, I know L is liters. This kPa, initially I'm not sure what that is, but I read this, is allowed to expand at constant temperature, which means the temperature is not changing, until its pressure is 101.3 kPa. So by reading this, this should tell you that kPa is a unit of pressure. So the units that we use for pressure are, there's a lot of different ones. This is just another one we use. It's actually called a kilopascal. Like I said, you don't have to know much about where those units come from. You just have to know how to do the math. So we're going to do P1, V1, P2, V2. Let's get some values in here. And then we can set up our equation, which is P1 V1 equals P2 V2. All right, let's see. The pressure, this is a pressure, kilopascal, this is a pressure. So we have both of our pressures. If oxygen at 128 kilopascals is allowed to expand until the pressure is 101.3. So the pressure went from 128 to 101.3. So this is where it started, this is where it finished. So 128 kilopascals and then 101.3 kilopascals. All right. So we use both those numbers. I'm kind of done with them. The volume is 2.11 liters. Is this the starting amount or the ending amount of the volume? And you really have to read this. If oxygen at 128 kilopascals is allowed to expand at constant temperature until its pressure is 101.3 kilopascals and the volume is 2.11 liters. So the 101.3 and the 2.11 liters, they go together. So 2.11 liters. And then if we read this last part, what was the original volume? That's V1. That's our question mark. That's what's asking us. So remember, the 1s represent the original or starting amounts, and the 2s represent the ending or final amounts. Anyhow, you plug them in now. We just do some easy math. So P1 is 128 kilopascal, and the volume 1 is a question mark, so we'll just leave it as V1. P2 is 101.3 kilopascal, and the volume 2 is 2.11 liters. Okay, so all we have to do to solve for V would be to divide by 128 kilopascal on both sides. These will cancel. Here the kilopascals will cancel, but the numbers don't. And we see that our volume 1 will be equal to 101.3 times 2.11 divided by 128. And let me type that in real quick. 101.3 times 2.11 divided by 128. And we are left with a volume of 1.67 liters. The reason we know it's liters is because this volume was liters, so this volume must also be liters. The units should stay the same. Also, we canceled everything else out, so clearly it had to be liters. Okay, so that's it. We're just going to use this formula, this Boyle's Law formula. Once you plug in the values, it's just multiply and divide. It's pretty easy. All right, one more example for you. And we're going to solve this the exact same way. The pressure on 6.0 liters of a gas is 200 kilopascals. What will be the volume if the pressure is doubled? What will be the volume if the pressure is doubled? So we don't have enough numbers there, but hopefully we can figure out enough information. Let's do P1, V1, P2, V2. Okay. The pressure of a gas on 6.0 liters is 200 kilopascals. So we have the initial amounts. The 6.0 liters, that's the initial volume. And the 200 kilopascals, it's right there. Okay, what will be the volume? So after something happens, what will be the volume? That's our question mark. If the pressure is doubled. So if the pressure was 200 kilopascals, the pressure will double to 400 kilopascals. What will happen to the volume? So anytime we're comparing pressure and volume, we go right back to this formula, this Boyle's Law. Pressure 1, volume 1 is equal to pressure 2, volume 2. We can plug in our numbers and solve. So 200 kilopascals times 6.0 liters equals 400 kilopascals times V2, that's our question mark. So now we want to solve for V2, so let's divide away the 400 from both sides. These cancel. Here, the kilopascals, the units cancel. So now I have 200 times 6 divided by 400. Let me type that in really quick. And the volume goes from 6.0 liters, and once the pressure is doubled, the volume gets cut in half to 3.0 liters, and that's V2. Sorry, that's not the best 3, but you get the point. And that makes sense. That's what I told you the other day. The pressure and volume are inverse. So look, if the pressure got doubled, the volume has to get cut in half. We probably could have figured that one out without doing the math, but that's okay. So, like I said, on Schoology, you're just going to have a couple of these problems, maybe 2 or 3, not much. And just type in the answers. And that's about it. Let me know if you have any questions. I am going to have some online study sessions this week where we will be able to talk face to face, so I will send you messages to let you know when those will be happening. All right, have a good day.